Hello and welcome to the first day of the 7th week of the lecture series. So last week we started looking at the molecular vibration and its symmetry properties. So just a quick recap of whatever we discussed in the last class. So we mentioned that there are different degrees of freedom available for a given molecule. So out of this three different degrees of freedom that we know about, one is translation, one is rotation, another is vibration. And this part of the lecture this week or little part of the next week also will be dealing with this molecular vibration and their symmetry properties. So we mentioned that molecule can vibrate, its bond can stretch, its angles can bend, and it can go in a plane or out of a plane. So different bonds will make different kind of movement, different angles will make different movement. So apparently it may look like that it's a random motion, but if one takes a close look at these motions, then one will find that in this randomness there is actually a symmetry involved. There is a regularity there, and this this seemingly aperiodic or random internal motions of a vibrating molecule that are the result of superpositions of a number of relatively simple vibratory motions which are known as the normal mode of vibration. Now each of this normal mode of vibration, they have their fixed frequencies, okay, and we need to know for a given molecule what are the normal mode of vibrations and what are their symmetries, so that we can develop something further in understanding this molecular vibrational motion and the energy transition from one vibrational state to another vibrational state, how it is governed by the symmetry rules. All right. So we started talking about the properties of this normal mode of vibration, and in that case, what we said is that each of the we actually defined the normal mode of vibrations for a particular molecular ion, which is carbonate ion. Okay, so we looked at, and this carbonate CO3 2 minus, and we depicted all the possible normal modes. So first we deduced what is the number of normal mode of vibration that is possible for this. So we also looked at the way to find out the number of normal modes for a given molecule, and we found that if the molecule is nonlinear, then 3n minus 6 is the number of normal modes, where n is the number of atom in that given molecule, and for a linear molecule the number will be 3n minus 5. So using that formula, we could say that for carbonate ion, which we are taking as a planar molecule, the number of normal modes are 6, and we drew all 6 normal modes of vibration, and we mentioned that okay, this normal modes are depicted by arrows, which tells us about the particular direction and relative magnitude of the motion of the atom involved, okay, in a particular direction, or change of angle because of this motion, both in plane and out plane. So we said that this 6 motions that are possible, that is 6 normal modes of vibrations, we given them discrete frequencies, right? That's a property of normal mode, that each and individual normal modes will have a distinct frequency. So we mentioned this one as nu 1, this one as nu 2, and this is nu 3 A, and this is as nu 3 B, while this is nu 4 B, and nu, sorry, this is nu for A and this is nu for B. Now it will be clear in a moment why we are calling this as 3A 3B, not like 3 4 5 6. Okay, there is a reason, and that is also given by the symmetry properties of these motions. Now there are two distinct properties of this particular, this type of motion, that is normal mode of vibration. That is, here this vectors that we are using to represent the motion of a particular atom or a particular bond in a particular direction, they can be expressed as a linear combination of the basis vector that we use. Okay. And second, that each one of these normal modes, so nu 1, nu 2, nu 3a, nu 3b and so on, all of them, each one of them will transform as one of the irreducible representation to which this particular molecule belongs to. So here this particular structure, if we look at, we easily can say that this molecule has a point group of D3H. If you remember your basics from this course, so it has a C3 axis and it has 3 perpendicular C2 primes and it has sigma h. This is this plane because we are considering a planar molecule. So it has a point group of D3H. So what it says is that each of this normal mode will belong to one of the IRs of this particular point group D3H. Right. Now we have to first ask that how to assign the symmetries of this these normal modes. Okay. So what we need to do for that? So we need to look at the effect of all the symmetry operations of D3H point group on these particular normal modes. So we'll look at this 1, 2 and 3A, 3B, 4A, 4B. So if we look at, say, first these structures for which the frequency is nu 1, we'll see that whatever be the symmetry operations. So what are the symmetry operations for D3H? So for that, if you want a quick answer for that, what you have to do, you have to look at the character table, right? You know by now that if you look at, so this is a form of character table, you can get it anywhere. So you look at the character table for, say, any particular point group. So let's look at the point group of D3H, all right? And so here we go. So if we look at the point group of D3H, you will find all the symmetry operations there. Okay, and the corresponding irreducible representations, the terminologies, you will also get the linear or non-linear functions which also transform as the the irreducible representation of this particular point group. So if I look at this, and we can easily figure out what are the symmetry operations that it has. So I will just quickly mention. So it has identity, it has C3, C3 square, it has 3 C2 primes, it has sigma H, it has S3 and S3 5, and it has 3 sigma V's, right? All right. So now what we have to do, we have to deal with the transformation of all these vectors that are representing the motion of these atoms within a normal mode of vibration, how they behave, right? So if you apply identity on this particular structure, what you will get, everything will remain unchanged, correct? So if you take this structure as a whole, fine. So if I can just redraw the same structure here, what I have, 3 equal arrows which are along the 3 bonds, okay, in the same direction of this CO bonds, right. So now if you apply identity, it will give back the same structure, all right. Now if you apply C3 on this motion, so if you rotate C3 and if you are not numbering them actually, just looking at their overall disposition of these arrows, then C3 also will give you the exact indistinguishable structure. So that will also give you same structure back. So if this gives me 1 and this gives me 1, and next you look at the C2. So C2 also, because after rotating about, say I am considering this as my C2 axis. So if I do a C2 around this one, so this will rotate, and since these are not numbered, so I have an indistinguishable structure. Okay. So ultimately after applying C2, you will get just an indistinguishable structure. So overall it will give me a character 1. And while I am writing these characters, I am reiterating that here I am not taking these 3 as separate 3 basis vectors, but as a whole this is my structure, and this is as if acting as one basis function, all right. So similarly sigma which also will give me 1 because there will be no change. S3 is also going to give me 1, so will sigma v. So looking at this character, you can find out that this is a totally symmetric irreducible representation. So what is the totally irreducible representation in D3H? Say that it gives a term A1 prime. Alright. So the same way, if you look at the structure nu 2. So if you look at the structure nu 2, what you see that 3 oxygen atoms are out of the plane, that is above the plane, while the carbon atom, central carbon atom, that is below the plane, that is given by the plus and minus sign. Okay. So plus means it's above the plane and minus is below the plane. So what happens here? So if you apply identity, so identity will give you say if I write down for this particular structure, say here, so identity will give me a character of 1, while say C3, that will also give me 1 because after rotation by 2 pi by 3 I will get an indistinguishable structure. So if I go for C3, that is also going to give me 1. Now for next is C2 prime. C2 prime is also going to give me the same thing. So C2 will give me character of 1, and then we have sigma h. So sigma h is going to invert the signs, right? So whichever was above the plane, they will now go below the plane, and whatever was the below the plane now will come up. So that will invert the structure. So it is going to give me -1, all right. And then we have S3. So S3 is what? It is the effect of C3, which doesn't do anything, but then there is a perpendicular sigma plane. So that is going to invert everything. So then again S3 is going to give me -1, and then we are left with sigma v. So sigma v is not going to change anything, right? So sigma v will give me +1. So now if I compare this particular irreducible representation, because here the representations are giving me only one as the matrix element, only one matrix element is there. So it is a one dimensional representation, and therefore I can just quickly check in the character table and find out which irreducible representation this one is. Okay. So only the character of sigma h and S3, they are negative, right? So if I compare that, then I have to so for D3H I have so here sorry, there was a mistake. This C2 actually, if you look at, so if I take this as my C2, so what's happening, this two are going below the plane, and so is this one. So every atom and their position is getting inverted for C2 as well. All right. So the C2 primes. So therefore, what we have is C2 is also giving me -1. So that was a mistake. So if I correct everything, so now I have C2 sigma H and S3 as -1. So now let's compare. So that gives me A2 double prime. So this belongs to A2 double prime. All right. So now what I can see that both of these normal modes that we considered, when we operate the symmetry operations, we are finding that they transform according to one particular irreducible representation. The first one we found it to be A1 prime, and this one now we are finding to be A2 prime. So in this way we can keep going on. So here, like this nu 3a and the structure corresponds to nu 3p, they actually form the basis for the irreducible representation E prime together. So that can be shown, and we will show that real quick shortly. So what we can think of is the following. So when you apply the symmetry operation, say for example C3 on this one of the structures nu 3a, so what it will do, it will transform to a new configuration, which will be nu 3a prime, say for example. So what will be the form of nu 3a prime? So what we are saying is this nu 3a prime will be a linear combination of nu 3a and nu 3b, and similarly nu 3b, when we operate any symmetry operation, that will also be a linear combination of nu 3a and nu 3b. So let's show how it is going to work. So here we are showing an example how that C3 affects this structure with nu 3a. So this is the one. So after operating C3, what will happen? So this arrow here on this atom 1. So here when we are doing this operation, so we are only dealing with this vectors. All right. So this guy will now go over here, right? So accordingly its orientation will also change. Now you see this one, which was on atom A, is now coming over here with this orientation, and this guy on the carbon atom, this big arrow, will now go to a particular 180-degree direction. So it will come somewhere here, and let's have a look at this. This is the new position of this arrow. So in this way you can find out what will be the final structure. Now this final structure, which we are calling as nu prime 3a, how we can express this in terms of nu 3a and nu 3b. So if I say that this new structure, that is nu 3a prime, is expressed in this fashion, and if we can show that and prove that, then we have proved our point. So you take a particular mode of normal mode of vibration, so you take part of it. So here, like you take you look at the structures nu 3a and nu 3b. So you see here, all right. So this one, if we operate and you will get an ultimate structure that we have just shown. Now if you take some portion of this one and some portion of this one and can generate that resultant nu prime 3a, then our job is done, and that's what is shown here. So if we say that minus half of nu 3a plus half of nu 3b is equals to nu 3a prime. So this is a linear combination of this. This is some sort of combination. So what is minus half of nu 3a? that is this one. So if you take the original structure, the arrow, and if you apply this minus half on that, so you will get this structure. Similarly, plus half of this nu 3b will give you this. So you will see that this length has been reduced to half of its original length, and here the length has been reduced to half of its original length, as well as the direction has been reversed because the minus sign. And now if you add this two, you get this one, which is, if you compare here, you see this one. So you could express this new structure as a combination of this nu 3 and nu 3b. Similarly, for any other particular motion on any particular atom, say 1, 2, 3 or 4, you can express them in this particular fashion. So this is true for this whole normal mode, right? So all these things are like breakups of those individual arrows that are situated on each and every atom, and you take this particular combination rule, and you see that ultimately you can generate this structure starting from nu 3b. Similarly, you can show that for nu 3b, and there will be another type of combination where here this nu 3a prime is a combination where it's minus half nu 3a plus half nu 3b, and for say for nu 3b, if I operate C3 on that, so that I can write as minus 3 by 2 nu 3a minus half nu 3b. Okay, so in this combination I can express the new form of nu 3b after operating C3. All right, so in this way, if I can show for the nu 4a and nu 4b also. Now what does that mean? Mean that nu 3 and nu 3b upon the symmetry operations on them, they cannot transform in as one of the irreducible representation of D3H point group alone, but together, that is nu 3 and nu 3b, together they can form the basis for a particular representation, and that must be a two-dimensional representation, because we are taking two basis function as if, right? So nu 3a and nu 3b together, they will form two-dimensional irreducible representation. And if you find out all the operations, the effect of this all the operations on nu 3 and nu 3b, you will see that it belongs to it forms a basis for E prime representation of the D3H point group. And ultimately you can see that all the normal modes they form the basis for irreducible representation to which for the point group to which the molecule belongs to. Okay, all right. So now here we started with showing the normal modes of a particular group, and then we showed that they have their symmetry properties. That is, they belong to they form the basis for the irreducible representations. Now, how do I, if I do not have this normal modes present in my in front of me, can we ab initio find the normal modes and its symmetry properties? Okay, so we can show that by using the same particular molecule. So how do we do that? So first of all, we need a set of basis functions, right? So we can do that in two ways. Because we are dealing with the molecular the internal motion of the atoms and the bonds in a molecule when we talk about vibration, then we can actually take the all three Cartesian coordinates sitting on each atoms of the molecule, because we stated at the beginning that all these arrows, right, all these motions of these individual atoms when they execute one particular normal mode of vibration, this each arrow can be expressed as a resultant of three basis of the resultant of the basis vectors that we choose. So if we take x, y, and z coordinates on each atom, so this arrow which defines of the part of this normal mode, that can be expressed as some sort of combination of this x, y, z. So what I mean is following. So if I have, say, let's just say tell it like this. So I have all right. So now in one of the motion that I showed like this, what I say is I can take this x, y, z, and take this atom to be sitting at the origin. All right. So then if I take the coordinates accordingly, then this particular arrow I can express as some sort of combination of these basis vectors. So I can take the Cartesian coordinates of all the atoms. Okay. So and in each case, what I will do, I will take the atom to be sitting on the origin, and I will consider their x, y, and z coordinate system to be acting as my basis. So therefore, what I can do, for this one I will have total 4 atoms, so 4 into 3, total 12 basis functions, right, in my set, and we can do whatever we want to do on that. The other option is that we can take the internal motion of these molecules as such. What do I mean? So here what I do is, like, I have these arrows defining my internal motion, right. So suppose I take this carbon oxygen bond. So by this arrow, what I say, that this oxygen is moving away from carbon. So in other words, this CO bond is getting stressed, right, or when it is coming back, then it is it's reducing the bond. So I can also take the angle between these two CO bonds. So I can take this angle as one of my basis functions. I can also take a dihedral angle, meaning that I have a sigma plane here and I have this angle here, okay, or I have this plane here and then I have this bond here. So the angle between that, I can take all these internal coordinates to be my basis function, and we will show in the following class that in either of the cases I can get the required information, and in certain cases without knowing or with this simple use of symmetry, I can really talk about what are the particular normal modes that this molecule have. So in other words, I can draw the exact normal modes of these molecules, of any given molecule. So that's what we will start with in the following class. Till then, thank you very much for your attention.